This is Unit 2D, Example 5. So make sure you take a minute and read through the introduction to the normal distribution curve. This is the bell curve that we'll use very often in statistics. Notice that it is symmetric, so we don't have any skew relationships with the symmetric normal distribution. And then its function is quite complicated. You can see it involves the standard deviation sigma. It's got a square root. It's got 2 pi. It's got base e in it. It's got mu for the mean in there. It's got squares. It's got negatives. So we're going to rely on technology to work with this equation since it is quite complicated, and even calculating areas with this equation gets messy. So we rely on using a computer or a graphing calculator to calculate or approximate the areas for us. Like other distribution graphs, the area under the curve adds up to 1.00 or 100%. And then all of the y values are positive, right? That's our other requirement to be a distribution graph. An important thing to notice is in function notation, that sometimes this normal distribution curve is called f of x or p of x to indicate that the output, we sometimes think of it as a probability, or you'll see also the Greek letter phi. This is phi, the Greek letter, in function notation. But again, it's just the function notation as another way to write y, or the output. So in example 5, we're going to compare two graphs here, and there's a graph on the left centered at 0, and the graph on the right in green on my screen is centered at 5. And so they're both normal distributions. They both have the bell shape. They're both symmetric. And so we want to think about, well, how are they similar and how are they different? And it looks like they're just copies of each other, but shifted in different directions. So we can say both graphs are symmetric, bell-shaped normal distributions. They have the same height of their peaks, and they both have a range of about 10 units. If you look at the blue graph centered on the left, it looks like the range goes from -5 to +5, so around 10 units for the range. And then the graph on the right, that's green on my computer, centered at 5, goes from 0 to 10. So again, that also has a range of about 10 units. So the difference in these graphs is they're centered. So the left blue graph is centered at 0, and the green graph on the right is centered at 5. So the mean determines the center of the normal distribution. Remember, when a graph is balanced and symmetric, the mean and the median are in the same place. If you look at the blue graph centered at 0, imagine if we chop this in half, you're going to have 50% of the area of the graph on the left and 50% on the right. Okay, example 6 compares standard deviation. So take a minute and pause the video and read through this paragraph if you haven't already. Notice that we use this Greek letter sigma. It looks like a circle with a tail on it. It's a lowercase sigma. It makes a S sound in Greek to represent the standard deviation. So here again we have two graphs, and on my computer screen we see the graph with the higher peak is blue and the wider graph with the lower peak is red. So we want to think about how are these graphs similar and how are they different. So both graphs are symmetric, and they're both centered in the same place here at 50. The red curve, the wider curve here, has a wider spread than the blue curve. And in part C, we'll actually calculate what the range is from the lowest point to the highest point for these two graphs. But we can see it looks like if you were transitioning from the blue graph to the red graph, imagine putting your hand on top of the blue graph and pushing it down to squish into the red graph. Question B asks, which normal distribution curve has the greater standard deviation, and how do we know? So we know the red curve, or the wider curve, has data further from the mean, right, because they both have the mean or median at 50. And so it makes sense that it's going to have more variation in the data. So the red curve has the larger standard deviation. Another way to consider is that the curve with the larger range, in this case the red curve, has greater standard deviation because the dispersion is further for the data values. So the data values are dispersed further throughout the graph. Question Question C asks us to calculate the range for each distribution graph. So you can estimate the endpoints as best as you're able. So if we look at the red graph, that's the wider graph, it looks like it goes from 10 to 90. So the range is about 90 minus 10, or 80 units. The blue graph is narrower, and that goes from 30 to 70. So that range would be around 70 minus 30, about 40 units. And I'm saying units here because we don't know what we're measuring on this graph. It may be, if we know that we're measuring test scores or heights, then we would give those units associated with the graph. Question D says we know that the area under the normal distribution graph must total 1.0 or 100%. Again, this is fitting the definition of being a distribution. So how does the graph with smaller standard deviation compensate so that both graphs have the same area? Well, if we look, the peak of the blue or the narrower curve centered at 50 is higher than the peak of the red, which is the wider curve. So the blue or the narrower distribution graph has more area around 50, whereas the red or the wider distribution graph has the area spread further out along the graph. Example 7 introduces what we call the 68, 95, 99.7% rule. So all normal distribution curves have the same bell shape. They might be stretched or compressed in different ways depending on the values for the standard deviation. But we see in this graph it's centered at 100, and so we see if we go down one standard deviation, we've gone down to 90, and if we go up one standard deviation, we've gone up to 110. So this graph has standard deviation of 10, and 68% of the data fall within one standard deviation. This is true for any normal distribution graph. So once you label your mean in the center and use your standard deviations to label, you can figure out where the 68% of the data lie. In the second graph, you'll see, I like to draw it this way, broken up into chunks with the percentages. So you'll see I took the 68% and broke it into 34% on each side of the mean between -1 down 1 standard deviation and +1 up 1 standard deviation. If we come out 2 standard deviations, we can see we're trapping most of the area of this normal distribution curve, and so that has 95% of the observations, or 95% of the data. And so that leaves us, you can see, 2.5% on the outside and 2.5% on the lower outside, so that the total, if you add 2.5%, 95%, 2.5%, is 100. 3 standard deviations, you can see it looks like we have almost all of the data, and so that covers 99.7% of the observations. Later on, we'll develop some tools to get more precise, but for now, we'll use these values to estimate. And again, I find this picture helpful, and you can see we know to capture 99.7% of the data, there's 2.35% on this side between 2 and 3 standard deviations on the negative side, and 2.35% between +2 and +3 standard deviations. That leaves an extra 0.15% of the data outside on either tail after 3 standard deviations. We never say we've captured 100%, because imagine if this is a graph of heights, you could always have someone come along who's taller. So we never want to say that we've captured 100% of the data inside the graph, because there could always be someone taller or someone with a slightly higher test score, unless it's something where it's fixed at a certain max or min value. So earlier we looked at the vocabulary test scores for 7th grade students in Gary, Indiana. And so that distribution was close to bell-shaped, so we call it approximately normal. We do this very often. If the graph is close to normal, we can go ahead and say it's approximately normal and use our normal distribution to calculate approximate values to give us guidelines. So that graph from the 7th grade vocabulary scores had a mean score of 6.84 and a standard deviation of 1.55. And notice we're using the Greek mu for the mean and the Greek sigma for the standard deviation. So we want to know, what's the range of scores for 68% of the data? So 68%, remember, is up and down 1 standard deviation. So we take our mean and subtract 1 standard deviation. So 6.84 minus 1.55 gives us 5.29. So we call that our lower bound. Our upper bound, we start again with the mean and we add 1 standard deviation to get 8.39 as our upper bound. So we can say 68% of the scores fall within scores from 5.29 to 8.39. So now if we want to think about the range of scores for 95% of the data, when we calculate our lower bound, we're going to start with the mean, and then we're going to subtract 2 times the standard deviation. And remember, the order of operations is going to multiply 2 times the 1.55 first, and then subtract that from the 6.84. So we get there a calculation of 3.74. For the upper bound, we're adding the 2 standard deviations. So this becomes 6.84 plus 2 times 1.55, or 6.84 plus 3.10, and we get to 9.94. So we say 95% of the scores fall within 3.74 to 9.94. And then we might ask, what score is the cutoff where 2.5% of students score higher? So if we look back at our normal distribution chart here, remember there's the extra 0.15% out here after 3 standard deviations. So the 2.35% and the 0.15% total up to that 2.5% outside of 2 standard deviations. They're asking the 2.5% of students scoring higher, so that's the top 2.5% of scores. So that must fall at this upper bound for the 95% cutoff. So that is 9.94. So we can say the top 2.5% of scores must fall at 9.94 or higher, but we say plus 2 standard deviations. And again, notice the percent between 2 and 3 standard deviations is 2.35%, so there's an additional 0.15% that we're counting after the 3 standard deviations. Part D asks, what percent of scores are higher than 5.29? So remember, 5.29, if we look back, was the lower bound for 1 standard deviation. So we know there is 68% within 1 standard deviation. So if we do 100% minus 68%, that leaves us with 32%. But remember, that's divided between 2 tails. So they're just asking about higher than 5.29%. So we can think about the complement idea and think about, well, how much is less than 5.29%? So if we take that 32% in the 2 tails, divided by 2, we get 16% falling below 5.29. So we know, now they're asking about higher than 5.29. We know everything totals 100% under the normal distribution curve. So we can say 100% minus 16% to tell us 84% of scores are above 5.29%. And we're using this fact, we know that the total area under the distribution curve is 100%. So again, this is the complement calculation, and the reason we use subtraction in situations like this is it's typically faster. You could have also come over to our helpful normal distribution chart with everything broken down and tallied up all of the values of 34, 34, 13.5, 2.35, and remember there's the extra 0.15% outside. And you would have got that same 84%. All right, let's look at example 8. There's a typo on my page, but it should say example 8. So here we're looking at data from summer monsoons in India. And notice we're told the mean is 852 millimeters, and the standard deviation is 82 millimeters. And so in shorthand, we write n like it's a normal distribution or it's in function notation. So we write the normal distribution is a function of 852 for the mean, comma, 82 for the standard deviation. So inside the parentheses, we indicate the mean and the standard deviation so that anyone could come along and recreate the graph. So to solve this, we could certainly sketch out the normal distribution curve, and that's often helpful to do. But we can also just think about the lower bounds and the upper bounds. So question A asks, between what values do the monsoon rains fall in 95% of all years? So 95% is 2 standard deviations, 95% is contained within 2 standard deviations. So our lower bound, we start with the mean and we subtract 2 times the standard deviation. So we get 852 minus 164. So our lower bound is 688 millimeters. Similarly, for the upper bound, we're going to start with the mean, add 2 times the standard deviation, and end up at 1,016 millimeters. So we can say 95% of all monsoon rains fall between 688 millimeters and 1,016 millimeters. So they use this data to figure out if certain years are extreme values. They do similar in California when they try to determine if we're in a drought. Is we look at the 68% range, the 95% range, and try to figure out, are we in an extremely dry or an extremely wet year? So question B asks, how high are the monsoon rains in the top 0.15% of years? So this would be real extreme values or real rare years. So the top 0.15% is the upper limit for 3 standard deviations. So we just need to find the upper bound here. So we start with the mean, 852 millimeters, and we add 3 times the standard deviation. And remember, order of operations, we're going to multiply 3 times 82 first. So we have 852 plus 246, and we have 1,098 millimeters. So we can say in the top 0.15% of years, the monsoon rains must have been higher than 1,098 millimeters. Question C asks, how small are the monsoon rains in the driest 2.5% of years? So the driest 2.5% of years are over at the other side of the normal distribution graph, right? These will be lower boundaries. So remember, the lower 2.5% is a lower limit for 2 standard deviations. So the lower bound is going to start at the mean, 852 millimeters, and subtract 2 standard deviations. And we see we get 688 millimeters. So in the driest 2.5% of all years, monsoon rains must have been less than 688 millimeters.